Hey Professor Ward, I'm Rishabh and I'm a member of Team 15 along with Nicholas and Servesh, and we are Radial Health. And this is our final presentation for our first semester of our Capstone course. So here's a quick table of contents and some medical background. This is the same medical background as the first and second presentation of the term, but nevertheless, I think it's a good idea to kind of reintroduce ourselves to the project and why it matters. So, kidneys. The key role of the kidney is nothing more but to filter waste and excess fluid from blood and produce it into urine. If a kidney fails, that's called kidney disease, and it's quite a prominent disease. 1 in 10 Canadians have kidney disease, and in the final stage of kidney disease, you need kidney dialysis. And this is needed when kidneys can't filter blood on their own, and we need an external machine to pump our blood for us so we can clean our blood properly. In order to do that, we need to make an AV fistula. So there's an artery called a radial artery, a vein, and we attach through a little bridge. This bridge is called an AV fistula, and it allows us to kind of create this access point more easily so the procedure can work properly. However, we have a relatively high rate of failure here. In Ontario, the 1-year survival rate for patients is around 80%, and the 5-year survival rate is around 40%. Why? Well, let's go to the fistula requirements to figure that out. For our AV fistula, it has to mature over time, so it has to expand in relation to the stuff around it. In order to expand or mature properly, it has to make sure that there's no failures in this fistula. These failures can be caused by two main things: stenosis, or a narrowing of the blood vessel, or thrombosis, a blood clot blockage. There's some current innovation in the space. Medical diagnosis has always been very observational, but attempts to add more quantitative metrics have been well underway. One of the initiatives is using CFD, or computational fluid dynamics, to predict key parameters like wall shear stress. Before CFD was introduced, typically AV fistulas have a 70% failure rate to mature after a year. However, after the addition of these CFD metrics, this failure rate dropped down to 10 to 20%. That's great. But what actually is CFD? Computational fluid dynamics is a study of how computer simulations can model how fluids, like blood, can flow through devices and vessels. It's used all the time in housing and construction to model the flow of air through a building, or in aerospace to model the flow of air through a plane, but it's rarely used in the medicine field. It allows us to spot problem areas, identify zones of low flow or high stress that can lead to clotting or vessel damage. Afterwards, we can optimize the design to adjust the shape or the incision point to optimize and reduce these problem areas, and this comes with an obvious patient benefit. Studies have shown that it reduces complications, prolongs access lifespans, and supports improved survival rates. That's great, but these studies have been conducted in top-class medical facilities around the world, and it's not viable for most clinicians and most hospitals. There's two main limitations. The first is that it requires specialized expertise. You need an expert engineer or physicist to come in and decipher the CFD simulations. That's not viable. And we can't expect doctors to also take the cost and the time to learn how to read CFD simulations. Another main thing is high compute time and cost. Patient-specific runs can take up to 6 hours and almost $2,000 per case. And with our current state of healthcare, that is not viable. So, that leads to our project abstract. Can a machine learning surrogate, trained on high-fidelity CFD outputs from patient CT scans and ultrasounds, predict key flow parameters like pressure, velocity, or shear stress in seconds with actually comparable to traditional CFD simulations? This matters because it enables real-time clinical decision-making, improves patient outcomes, and it lowers costs and resource burden. First, we'll talk about our two partners. Our first partner, our prof mentor, is Dr. Sean Peterson. He's a faculty here at University of Waterloo, and he's also a prof at MME. And he's running the UW Fluid Flow Physics group, mentoring us in the actual development of the models. And the person on the bottom is Dr. Aaron Fenster. He's a medical physicist from the University of Western Ontario, specializing in vascular imaging and image guidance. And fun fact, he's also one of the inventors of the 3D ultrasound. So, what's our proposed solution? We have this 4-step solution. Our first step is that the clinician starts off with a series of patient ultrasounds and CT scans, as they always do. Step 2 is that the platform turns these images into a 3D mesh. Step 3 is that the model is run and a prediction of these hemodynamic values on the new mesh is outputted. And step 4, these values are then used by clinicians to better inform their decisions. And our progress update. But first, before I get into that, I want to talk about our 3 key lessons learned from last time. I want to preface whatever I talk about later with this so that it makes more sense about the actual decisions we made throughout the last month. Our first lesson is to start small and focused. Our second lesson is to have big ideas are cool, but implementable ideas get done. And lesson 3 is that software must be built with scalability in mind, especially for a long-term project like ours. So let's remind ourselves of our startup term goals. Our first goal was to create an accurate model simulation of a vascular artery, like an AV fistula, with a neural network, like a physics informed neural network or a graphical informed neural network. And the prediction accuracy will be measured against performance of existing systems. Goal 2 was a generalized prediction of this model on unseen new datasets. And goal 3 was to complete our user pipeline integrating with Dr. French's existing 3D ultrasound techniques. Goal 1, to predict accurate AV fistula metrics. What's the progress? Well, we initially began with a double dataset of 6 meshes, if you may recall. However, we had no state-of-the-art or SOTA for ML models to compare against, so we really didn't have an expert opinion in this. For resolution, we transitioned into a carotid artery dataset from Prof. Aaron Fenster to make a proof of concept, and our SOTA, or state-of-the-art, came from Dr. Fenster's expertise of what is clinically acceptable error. And then we can create AV fistula data later if our proof of concept is successful. So, this carotid artery dataset from the University of Western Ontario is a dataset of over 600 carotid arteries in 3D mesh form. The idea was that having such a high amount of vascular meshes will be more than enough data for us to train a model. But you might be wondering, but wait, this is not the same data as the AV fistula procedure, and you're correct. But again, the main idea was just to prove that it's possible to build an ML model to predict CFT metrics. After we do this, we can work our way up to a different data set and a different architecture. And I guess an update from last time is that UWaterloo approved our usage of this data set, which is a big W. And here is an architecture we used for quite some time. This is a graphical-based architecture, so we're only looking at the edges and the vertices of the whatever 3D mesh we're looking at. And in doing so, we predict TAWSS and OSI off of these graph-based features. So we're not looking at the physics, only the actual graphical features of whatever vascular structure we're looking at. And here is in one of the outputs we got from the semester. It's not terrible. We could do better, especially because we only had 6 meshes, and we trained it on 5 and tested it on 1. But overall, that is kind of where we were with the original public dataset before we went into the carotid artery dataset. And our second goal was to ensure the model generalizes to new, unseen datasets. Proving good generalization at first was very difficult, and we thought that was because of a very small dataset. And our hope was that moving to a larger dataset will allow us to create a model that can be adapted easily to different geometries. But first, I want to get to a little side note. What actually are flow parameters or fluid parameters? Fluid parameters describe how our blood moves through vessels. This can be pressure, the force on the vessel walls, velocity, the speed or the direction of the flow, or this thing called Reynolds number, a flow smoothness indicator. And it tells us whether flow is laminate or turbulent. And there's also inlet or outlet conditions. We define how blood enters and leaves the vessels, and this can vary through patient's physiology, heart rate, blood pressure, viscosity, or even something as simple as whether the muscles around the vessel are contracting or relaxing, or they can vary with geometry. Different arteries, fistula versus carotid, diameter, branching, these can all change these inlet-outlet conditions. And these matter because changes in these conditions shift flow patterns and alter parameter values. That means that one size fits all models won't generalize well. That was huge. So before I get into more, I want to actually show you a very simple example. Let's take a simple cylinder like this. This is the simplest example we could possibly think of. It's just one cylinder constructed out of these triangles, and it's a 3D mesh. So Let's take our baseline flow parameters and conditions. Here, let's say we have a very low Reynolds number indicating steady laminar, and we have an inlet-outlet condition that is basically nothing. We have a very steady flow both in and out of this tube, and there's nothing really going on in it, and the wall itself is smooth. Here, the resulting CFD output will have a pressure which is highest at the front where the flow hits, gently lower around the sides, and a small drop behind. And the wall shear stress is fairly even with mild peaks to the side and lower behind the cylinder, and the OSI is 0 here because its direction doesn't flip because the flow is steady. And here it's obvious that a calm, steady inflow causes the stress and pressure patterns to be predictable and symmetric. However, let's change it up a little bit. What if we make the parameters and conditions a little different? Let's take the inlet and make it like a choppy river. We add some pulse and random wiggles, and the outlet condition will have it be at the mercy of the natural force of this flow. We'll let the flow kind of develop naturally with no strict pressure target like before. And our flow smoothness, our Reynolds number, will turn it all the way up. The flow is more swirly and energetic, while the wall is still being smooth. Here, the resulting CFD output will have a pressure which has deep, low pressure pockets behind the cylinder and bigger overall pressure drops throughout, more drag. And we'll have a wall shear stress that drops in certain regions and creates natural trails. And hotspots move towards the flow, peels off, and reattaches. And the OSI will be high behind the cylinder because flow direction there keeps changing over time. If you see, even in a simple example like a cylinder with slightly different flow, our resulting CFD output is entirely different. That's huge. That's something we didn't actually consider a month ago. We entirely underestimated CFD this whole time, and we treated it like as if it's nothing more than a simple number to predict using ML. Thankfully, Dr. Peterson was here to save us, and we realized our mistake. And our mistake was that jumping into a relatively complex 3D mesh, like a carotid artery right away, and trying to predict flow, we will have several critical issues going forward. Namely, A, we're not sure how this can transfer to other vascular structures, even more so if they all have very different flow parameters and outlet conditions. And B, each vascular structure we have from our data set of carotid arteries are all a little different themselves, as, of course, everyone's arteries, everyone's veins are slightly different. How can we be sure our flow parameters aren't changing drastically per geometry? So, effectively, our original approach will leave us with a model that is trained on geometries of hundreds of carotid arteries without the concern of the physics behind the fluid flow. Because remember, first, our original model was entirely geometric. That's what the basis of these results were. So we had an entirely geometric thing, and we assumed blood flow was constant all the time. This means our predictions weren't actually based on fluid dynamics and were very unscalable to other geometry types. So we asked ourselves, is there a way to scale our approach better where we take fluid flow into account for our predictions and we know it'll work for varying flow parameters and for different geometry types? The answer is yes. We have a new training approach now, and we have a network that now learns a function of the flow settings along with the geometry. See on top, we take things like Reynolds number, inlet, and outlet conditions into the actual thing, and we create a context vector. And our final output is a concatenation of both the flow settings, the flow parameters, and the inlet out conditions, and the actual geometry, the stuff that actually makes up the mesh itself. And our prediction, our TAWSS and OSI, comes from both the flow settings and the geometry. So now, training the same vessel, like our cylinder, will yield different CFD outputs than when the fluid parameters change in accordance to the reality of physics. Now, we are going to run these models on small, simple meshes to begin with, then ramp up complexity of meshes as we iterate through the model itself. This will allow us to create a smaller suite of models that we will know that work for varying mesh types. Because ultimately, our main goal is to prove that we can create an MO surrogate for CFD simulations. If we can first prove that we can take the simplest CFD simulation, create an ML surrogate for that, then that must mean we're doing something correctly and we can scale properly. And also, it gives us, Team 15, a chance to actually learn CFD. Because at the end of the day, this is a brand new field for all of us. We aren't physics students, so this is a great way for us to also learn over the course of the fall term when we're all in co-op. So, before I get to the actual demo that Nicholas is going to show off, How do we make use of the actual model predictions? Well, we have some key metrics here. OSI and TAWSS. So, OSI quantifies directional changes in wall shear, and higher OSI indicates disturbed flow. And TAWSS, aka time average wall shear stress, measures mean shear stress magnitude, and lower TAWSS suggests low flow regions. And through this, we can quantify vessel openness through both these uh, figures. So we have arterial openness. Combining OSI and TWSS map where the vessel is well perfused versus prone to flow disruption. As I said before, the main causes for AV fistula failure of maturation is thrombosis or clot formation and stenosis or vessel narrowing. High OSI and low TWSS zones is an increased risk of thrombosis, and persistent low flow areas is an increased risk of stenosis. And through that, we can actually predict the maturation probability. And from that, we can select certain surgical sites that will lead to the highest possibility. This has been done in studies before. All we need to do is make sure that we predict the correct TAWSS OSI zones. So now I'll shift you over to Nicholas. He'll kind of show you through our GitLab and what we've been up to so far.
So my name is Nicholas. I'll talk a little bit about our repo. So this is the root. From root, our abstract is in docs. Also, we've used GitLab for tracking issues. And there's a bit of it here, but we kind of went back to Notion because some of our team members couldn't access the our GitLab because they're not from UWaterloo. So we went back to that. So later we'll add a screenshot here in docs for that. Okay, so then we have source. In source, this is essentially each folder other than papers corresponds to an experiment that we did and has code inside. And then each of these will also have its own info.md. So if you're ever confused, you can just look at that. Okay, so I'll start off with what we had before the midterm. And essentially all of that is in pipeline. So pipeline has all of our previous models, and you can find out information about that here. And you can go inside the notebooks and check out the code. And it looks like this, and then it has all the diagrams that we put on the slides. All of that is from these notebooks, so all that will be here. Right. So the next part is so we have the recalibration results. And then so here we tried fitting different lines. And then we have experiment summary. Right. And then next part is kind of what we added since the midterm. So the main few things are, first of all, visualization. This visualization essentially is we're just visualizing the TAWSS results. So we just basically color the nodes based on their magnitude of TAWSS values. So this is what it looks like here. And then the code to generate that is here. And then again, we have an info.md just to summarize. We also have a flow encoder. This is another thing that we've worked on. One of our goals was to be able to generalize to other data sets. We realized that we couldn't really do that with our model because we didn't capture the flow information. And that was something that we discussed a lot with our mentor, Sean Peterson, and he kind of told us about kind of how we were lacking in just showing or making use of the flow information, because with a given mesh or model, you can have many different like flows. So for example, you can have like the inlet condition, the velocity going in could be very different, and you could have very different results, right? And that was something that we didn't consider. Essentially, what we would have to do with our model is every time there's a new simulation, we would have to train again, and training is quite expensive, and we don't want to do that. So we don't want to do that every time. So essentially, that's what our flow encoder does. You can find more information about it in the .md. And then we have a basic prototype here, which does contrastive learning and then fits these points in space so that more similar points are closer together. So for example, all the channel family are together here. And then this is useful because later down the line, when you're training, then you can kind of then you can specify into the model what flow conditions do you want, and then the model, because it's been already kind of trained to distinguish kind of what flow conditions lead to what kind of results, it'll essentially help you generalize to different flows. So that's there. And again, we have an info.md just to summarize that. And Rashad will talk about this a bit more. I just gave a basic summary here. Finally, we have papers. These are just some papers that we've read. The main ones, we've read a few. We've read a lot more that we just kind of discarded or didn't really use. But essentially, you go in, and then there's going to be the paper and then the .md file. Right. So now that I've gone over all of this, next step is to kind of talk about the courses that influenced us or helped us throughout this course. One of them is CS479, which talks about neural networks. One of the most important things in neural networks was this idea of a deep neural network, right? And essentially, the benefit of a deep network, right, is that you're able to more easily capture information. So a deep network will converge much faster than a very shallow network, right? Because you're able to capture hierarchical features, right? And that helps us a lot. The other thing that helped us was this idea of the encoders. So here in CS479, we talked about autoencoders. That's the main one, I guess, that you would learn first because it's the most basic. In autoencoders, you basically you take a representation, you compress it into a very small vector, and then you kind of try to rebuild whatever information what it was, and then that reconstruction loss, essentially, you're trying to minimize it, right? And we use that in our flow encoder, not the same autoencoder, but we used info NCE. So here you're encoding the flow information here as a vector, right? In CS480, a very useful thing that we learned here was contrastive learning, right? And that's essentially the algorithm, right? Info NCE that we used for unsupervised learning, for the points for us to kind of cluster the points, the more similar points together by the physics features. Finally, CS484. In this course, we kind of talked about different algorithms for working with images, and that's kind of the main model. Was just images, and there are two main problem types, which were segmentation and classification. Right. So classification was essentially each pixel of an image you will classify as being in a particular class, right? So for example, if you have a data set where you're labeling, I don't know, maybe you have people or trees or dogs or other animals, you essentially label each pixel, and then essentially later on, given a new image, you're going to predict the classes of each pixel, right? And this idea of predicting unit values, so for an image, the unit would be a pixel, but for a mesh, the unit would be a node, right? Kind of setting that up, setting it up to predict unit values, and how to set that up, that experience really helped us for when we made our models here in the pipeline. So yeah, those were the three courses that helped us the most.
Hope you had fun with Nicholas. Now let's talk about our fall term deliverables. Here for the fall term, we're going to be taking, all of us, the CS494, or the part 2 of this course in winter 2026. So our goal for the fall is to work and build a strong base, so in the final 4 months of this, we can really build something really cool. So for the next 4 months, we want to continue to iterate on our model, increasing the complexity of 3D meshes with varying types of flow. Our general workflow will be to A. Create simple meshes with varying flow types, running CFD simulations to generate ground truth. Run the model on the mesh with flow parameter arguments, testing error and iterating on the model. And the goal, as I said before, is to have a smaller suite of models, each respectively adapted for various well-known CFD problems. Once we've done that, hopefully by January 2026, we will work with Dr. Pearson and our clinical partners to ensure the development of our model for AV fish loss and that has equal amounts of geometric and physics-based backing behind its predictions. As I said before, this is a project done in collaboration with Water AI, Waterloo's student design team. The team is split up into two, and all three members, me, Nicholas, and Sarvesh, are all on the neural network team working on developing neural networks for meshes. The other people on the team, the CFD team, are working on actually running the CFD simulations. So creating these simple meshes and running the CFD simulations for us to get the ground truth. And with that, I thank you for your time. That's the end of our presentation. And if you want to kind of learn more and kind of keep up with what we're doing, we have a website to the left and a blog to the right. Thank you, and see you in January 2026.